Hello, this video is going to introduce how to do nodal analysis, which is a circuit analysis technique that aims to find the voltages at different points in a circuit. And so this nodal analysis mainly relies on Ohm's law and Kirchhoff's current law to analyze voltages at different nodes in a circuit. So nodal analysis can be broken down into a few big steps. So the steps for nodal analysis include, uh, so step one, we can say, is assign variables to nodes. Well, what does this mean? So when we're starting with a circuit, we don't know what the we don't know what the voltages at most of the nodes are. And so we are going to assign variables to represent the voltages at those nodes. And this includes a ground point. And what the ground is a reference for 0 volts. So we need to assign one part of the circuit to be our 0 volt point, and all the other voltages, all the other nodes and the voltages at those nodes will be referenced to the 0 volt point we assign when we're doing this. And now there's tricks to make it easier to do these calculations by assigning the ground node at certain points, but um, I'll get to that later when I work an example to show this method. So first you have to assign variables to nodes. Now the second step in nodal analysis is you have to write Kirchhoff Kirchhoff current law equations for each of the nodes. So write KCL equations for each of the nodes. So for each node. Now remember, Kirchhoff's current law deals with the current going in and out of a node, and so for nodal analysis, it's appropriate to use Kirchhoff's current law along with the variables we determined earlier to write equations for the current or each node. And this will use Kirchhoff's current law, the nodal voltages, and Ohm's law. And then after we write these equations, we'll have a system of equations which we can solve. It's just step three. So solve the equations from step two for node voltages. So again, this is the aim of nodal analysis, is to find the voltage at different points along a circuit. And so after we do steps one and two, we are able to solve the equations to find what the voltage is at certain nodes. Now, you have to be careful for this because node voltages will depend on where you choose your ground reference point. So if you choose a ground point at one place, all the voltages at the nodes are going to be relative to that ground reference. And so node voltages will depend on different ground reference points. However, just because the node voltages can change, the voltages across components will not change. And what I mean by that is, let's just say you have like a resistor that has 5 volts across it. So if the resistor has 5 volts across it, it will have 5 volts across it regardless of where you choose your ground node. And so the resistor will always have 5 volts across it. For example, like maybe your voltages from the nodes come out to be 5 volts and 10 volts across the resistor. There's still going to be a 5 volt drop, or your nodal voltages could be like 1 volt and 6 volts on the other side, on both sides of the resistor. But wherever you choose your ground point, there's always going to be the node voltages can change, but the component voltages, so the voltage drop across components or voltage rise across components, will always stay the same. And so that's why you can choose any node as your ground node when you're solving for node voltages in nodal analysis. So now I'm going to work an example of how using nodal analysis to analyze a more complex circuit. So here I have a circuit that's more complicated than just a single loop or any like resistors in series or parallel. It's still a relatively simple circuit because there's very few components, but it's not trivial to where you can analyze it just using Ohm's law and some properties of resistors and resistor configurations, or at least simple ones, to be able to solve for like the current or voltage across each resistor in this circuit. And so we can analyze this using a multitude of different techniques, and I'm going to demonstrate how nodal analysis can be used to analyze this circuit. So, following our steps in nodal analysis, first we need to assign variables. And like I said, this includes assigning a ground point. So we have to assign one node as our 0-volt reference. And so the trick to doing this is we want to assign the node that has the most branches coming out of it to ground, because then the 0-volt reference will be related to the most number of different other. So if you assign a node with the most number of branches as a ground node, then there will be more nodes that are directly referenced to our known ground node, and that can make analyzing the circuit a bit easier. And so for this circuit, we see that there's two main nodes. There's one down here and there's one up here. And then we are going to assign the bottom one as the ground node, because this is the negative side of both batteries. And so it seems to make sense to assign this one as the ground node. And remember that this is the ground symbol, which looks like a triangle made up of 3 lines. And so this is our 0-volt reference. Another thing that we need to do that's not I didn't mention above is that we need to assign nodes on either side of a power source. So right now we only have voltage sources, but for like voltage and current sources, we need to assign nodes directly on either side of them. So there's a node here, but between these two nodes, you have a battery and a resistor in a branch. And we can't leave it like that. So we need to assign a node directly on either side of a battery. So we need to have a node here and then a node here, because we need nodes on either side of a battery. We can't have a node with a battery and a resistor between them like this in series. And so we now have 3 remaining nodes. And so we can call this first one V1 and the second one V2, because I already have batteries V1 and V2. So I'm just going to label them like this to help it be less confusing. And then we have our final node here in the middle. So this is node V3. And now we've completed step 1, which is assigning variables to each of these nodes. And one more thing we can do is we know this is referenced to ground. And so we can directly say that since this is 0 volts and there's a 5-volt battery here, we know V1 is 5 volts. And we know V2 here, since this is a 9-volt battery directly connected to ground here, is equal to 9 volts. So really, we only need to solve for V3. And now this is where we get to step 2, where we apply Kirchhoff's current law, KCL, to equations between nodes. And so we see here that we can analyze the node here. V3 is what we're trying to find. So now using Kirchhoff's current law, let's assume here, let's state that all the currents are going to be going in this direction here, like this. So going into the node. And then remember that Kirchhoff's current law, so we have KCL here, states that the assigned currents into a node, so the currents in a node is equal to 0. The sum of all the currents, the signed currents is equal to 0. And so what signed current is if it enters a node, it's one sign, and if it exits the node, it's the opposite sign. So in this case, if we're going into the node, then all the current going into the node is positive, and all the current going out of the node is negative. And that has to be equal to 0 because of the conservation of charge. And so we have these three currents here that I can label. I'm going to label this I1, this I2, and this I3. And what Kirchhoff's current law states is that I1 plus I2 I1 plus I2 plus I3 is equal to 0. All right, now we have that. Now how do we get I1, I2, I3? Well, this is where we use Ohm's law. And so using Ohm's law, we know that I1 here, Ohm's law, remember, states that voltage is equal to current times resistance. So current is equal to voltage divided by resistance. And now this voltage and resistance, we can see from the circuit, the different branches of the circuit. So for I1, we see that I1 is equal to the voltage divided by resistance. And so we have a resistance here, R1, and then a voltage is 5 minus V3. Because we want the current in this direction, it's the voltage divided by the resistance. So that's the current in this direction. So we have the voltage difference again is 5 minus V3. So that's the voltage from this point to this point. The difference in voltage between these 2 points. And then the resistance here. And so again, if the current is flowing into the node, we know that this has to be the we're subtracting so we're subtracting V3 from V1 because the current is flowing from V1 to V3. And so we're trying to find that difference. So you need to make sure that the order of these is right. And so for I1, we get that this voltage difference, 5 minus V3, is going to be equal, and then, well, that's equal to I1, but we have to divide by the resistance. And the resistance here is R1. And so we get these currents by analyzing the branches between nodes. And so we have I2 here is going to be equal to, we see it's going into this node here, so we have to subtract V3 from V2. Because if it's going inward, then we're assuming V3 is less than V2, and we're trying to find the positive, this is going to be a positive current. And so, or we're assuming that it's a positive current here. So that means that I2 is equal to 9 minus V3 divided by, and sorry, I'm going to replace R1 with 3 ohms because then we have numerical values to work with. So 3. I2 is 9 minus 3 volts divided by the resistance here, which is 6 ohms. And then finally, I3 is equal to, again, we're assuming it goes into this node here. So we have 0 volts because this is ground, minus V3, because again, we're assuming current goes from this node into V3. And so if we're assuming current goes into V3, then we have to subtract the node that's not V3, or we have to subtract V3 from the node that's not V3. And so it's going to be 0 minus V3 over the resistance, which is 4 ohms. So I'm going to leave out the sign here. But now we have these 3 equations, and then we can plug them in into Kirchhoff's current law here. So we have equations for this node for each, so each unknown node, we have to analyze the, so for each unknown node, we only have one unknown node in this case, V3, we have to write equations of the current going from that unknown node to every other node connected to it. So we know that there's 3 nodes connected to this unknown node, so we have to write these equations for the current from each of these 3 branches. So these are the connections between nodes. And now we have to make sure that we're consistent with our current too, because if this was also an unknown node, if we already determined I2 to be in this direction, then if we want to analyze this node, we have to make sure that I2 remains going in this direction, like that. And so once we establish the direction of a current, we need to make sure that it's consistent across the entire circuit. For the first one, you can just assume that like all the current is going in or out to make things easier. So if we plug this into the Kirchhoff's current law equation, we get I1, so 5 minus V3 over 3 plus I2, which is 9 minus V3 over 6, plus I3, which is just negative V3 over 4, is going to be equal to 0. And now we can solve this. So first I'm going to multiply everything by 12 to remove all of the fractions, or all the denominators. So if I multiply everything by 12, we get 4 times 5 minus V3 plus 2 times 9 minus V3 minus 3V3 is equal to 0. And then we can distribute these out and solve for V3. So we get 20 minus 4V3 plus 18 minus 2V3 minus 3V3 is equal to 0. And then if we move all the V3s to the other side, we get 38 is equal to 9V3. So 38 is equal to 9V3, and so that means V3 is equal to 38 over 9 volts, or 38 over 9 is also equal to 4.2 repeating, so like 4.222 volts. So this is the voltage at V3. We now know that the voltage at V3 is equal to 4.222 repeating. And so now, knowing this voltage, we can then solve for the other aspects of the circuit. So now if there were more unknown voltages, you would have to keep solving equations until you find all the unknown voltages. But now that we know that, we can solve for the other parts of the circuit. So like, if we want to find the voltage across R1, we just have to subtract 5 minus V3 here. So like 5 minus 4.222 is going to be equal to 0.777 repeating, but 77, we'll just put an 8 there to round it off. So the voltage across V1 is going to be 7.7778 volts in this from left to right. Voltage across R2 here, we get R2, so the voltage across R2 is going to be equal to 9 minus V3. So this is going to be 9 minus 4.222, which is going to be equal to 4.7778 volts. So we know that the voltage across R2 is going to be 4.7778 volts going from right to left. Now, from V3 to ground, we know that the voltage at V3 is already 4.222 volts. So this makes sense. So we have 4.222 volts at V3. So the voltage across R3 going from top to bottom is going to be 4.222 volts. And from this, we can see that I3 must be going out of this node instead of what we originally determined as going into the node. So we expect I3 to be negative, since it's actually in the opposite direction that we indicated it as. So we know that voltage R3 is going to be equal to voltage. So yeah, voltage R3 is going to be equal to 4.222 volts. Okay, and now if we want to see the currents across each of them, current across R1 is going to be equal to, well, we already have the voltage across R1, and so given the voltage across R1 and the resistance of R1, we can just say that current across R1 is equal to 0.777 0.7778 volts divided by 3 ohms, which is equal to 0.259 repeating, but I'll just round it off there. So 259 amps. Current across R2 is going to be equal to, so this is really just I2. The current across R2 is going to be equal to this voltage difference, which is, so current voltage difference is 4.7778 volts divided by the resistance of 6 ohms. And this is going to be equal to 0.7962 or 7963 rounded off. So 0.7963 amps. I'll round the other one to 4 decimals also. So this is 0.2593 amps for I1 and I2. Now I3 here, we are going to do it in the direction going out of the node. So the current across R3 going out of this node, so going from top to bottom, is going to be this voltage difference. So 4.222 divided by the resistance, which is 4 ohms. And so this gives us a current of 1.05 repeating. So 1.0556, I'll round it off, amps. And now to check, we can check that these currents actually obey Kirchhoff's current law. So we know that I1 plus I2 plus I3 is equal to 0. And since this current is in the opposite direction of R3, we know that IR3 is equal to negative I3, because IR3 is going to top to bottom, I3 is going bottom to top, and then I1 and I2 are in the same direction as IR1 and IR2. So plugging this in, we should get that, so 0.2593 plus 0.7963, so 0.7963 minus 1.0556 is equal to 0. And if you check this, this is indeed true. So since this is true, we know that this analysis turned out to be correct. And so we know that the voltage at this point is 4.222 volts, and then the currents and voltage differences across each of these components are shown here. So that is how you use nodal analysis to analyze complex circuits.